Okay, we now move on to a new lecture, a new practicum lecture about generics. Generics are a massive topic. Not only are they a massive topic, they're also a massively important topic. What does this mean? This means very simply that we have a lot of exercises and we will touch a lot of important, theoretically speaking and in practice, topics such as arrays, tuples, promises, etc. So brace yourselves. This is going to be long, it's going to be hard, it's going to be useful, and it's going to be fun. Okay, so we start with tuples. As you might remember, tuples are like an object with a series of values of different types, but we access them by position, 0, 1, etc. So we are required to define a tuple with a string, a number, and a boolean. Okay, that's quite easy. Const my tuple string, number, and a boolean. Let's also declare the type. String, number, boolean. The declaration of the type is quite intuitive, and if you look at this, you might notice that there's plenty of stuff happening in this type definition. We have the square brackets that are sort of signaling a structure, but we also have other types, so string, number, and boolean are other types, so the tuple type is defined by composing different types. Actually, the tuple is a generic type. The square brackets define indeed the content and the container, and then we put within the container the type arguments, which are other types. We could even have a tuple containing tuple. So we could say, no, the second element of the tuple are two numbers for whatever reason. There you go. So the square brackets of the first tuple, that's the container structure. The single arguments are separated by comma and are other types, and because a tuple is a type, we can also just put it in there. Okay, but let's move on and let's define a generic function that takes a tuple with a person and a generic argument. Print the generic argument next to the name of the person, and we have to define the type of person. Okay, so a generic function takes a tuple with two things, person and generic argument, unknown, and we print the name of the person and the generic argument. So let's do this. Type person, name and surname. Okay, and then the generic function. Print name and context. Okay, this is generic in an argument. I will call it A. You can call it whatever you want. Really depends on your, let's say, school of thought and where you studied programming, studied and learned programming. Like from the Java world or C#, you will probably call it T. In the functional world, you will probably call it A, B, and C, and so on. Oh my! What do I see? I see 4 tabs. No, not on my watch. Yes, okay. Okay, so we take as input the tuple. Just call it input. I'm being a bit lazy here. And the input will be a person and an instance A of the generic argument. And we can print. Well, you know that I prefer. No, okay, let's give it like this. I would prefer to just return something, to just return the thing to be printed, but you know, okay, for now we're going to go easy on it. Input. Okay, now the input, it's actually kind of funny. We have properties 0 and 1. 0 is person, 1 is A. Okay, so 0.name, and we also print the payload. Input of 1 And well, there's nothing to do here. Do you have at least 2 string? No. That's life. Now, print name and context of. Now notice that it's saying, okay, we have person and unknown as inputs. Let's start with the person. And we keep it autobiographical. And the second argument, let's say it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, now, notice that print name and context has adjusted, and the type argument that we're passing has now been inferred to be numbered. Very cute. We could have also turned this around and specified the type argument right away. I do prefer type inference whenever possible, and now the system knows, okay, the next element has to be a number because we specified it already. I don't like this, unless there's a very good reason to specify it, or the compiler is having some serious trouble understanding what is happening, which can be the case in many situations when the generic types become so complicated that it's impossible for TypeScript to just guess them easily also, or just complex to just guess them. Poor thing, it's doing a great job. Okay, and you see it's just printing. Notice also that there's nothing whatsoever we can do on this type, on this value, because only thing we know is it has type A. If we want to be able to do something with it, we will have to pass it as a lambda, but that is for later. Oh, very nice. Let's move on to arrays. Now, there's a note in the exercises that says avoid oh, wait, something weird is happening to my keyboard. Yes, avoid using library functions. So this is not an exercise in Googling. This is an exercise in programming TypeScript. If you use library functions, which obviously you will have to do later on in life, but if you do it today in this assignment, then you are going to miss the point of what you're supposed to learn. Also, library functions. Okay, this is my own personal take on this, but I find it very important that library functions that you use are things that save you time, not knowledge. Let me explain. So if you use a library function because you don't have time to write it and to debug it and to, package it properly, etc., but you could write it yourselves, then you're saving yourself time. If you're using a library function because you have no clue how that thing works, it's a black hole in your knowledge, and it's a piece of the program where you have no control over. And in that piece of darkness in your knowledge, there could hide some nasty bugs or some nasty properties that you don't know about that influence security, performance, or general reliability of your application. So it's good also to know exactly how library functions are implemented so that you can still use them because their convenience is super useful, but you're not bound to them. Anyway, we are asked to define an array of strings and to print all the strings in the array. Okay. Arrays are also generic types, and actually, even though there is a syntax, okay, so my strings, and we could say string array, this is something that I find absolutely ugly. I prefer uniformity in, I do prefer uniformity in code, and all generic types, with the exclusion of tuples and arrays, look like this. So name of the type, angle brackets, and generic arguments, and this is the syntax I'm going to use everywhere. Okay, A, B, C. Oh, missing a quote. Okay, and we have to print all of them. So let's do for, no, this was not a good idea. For of, yes, so for S of my strings console.log s. Oh, there you go. Okay. Also, we could have refactored this. Now, my strings dot for each, and then we take as input a lambda, takes s, call console.log of s. And there you go. I hope you've seen that there's actually a sort of direct transformation of a for off into a for each. And off we go. We shouldn't use map, because for each is not creating an extra array, and that's good. Well, we could also use map, but that would be quite silly. Why? Because map actually returns something, and this is returning an array of void. So we neatly save all the return values of console.log and just put them into a neat array. And an array of void is like one of the silliest things ever. Yes, you will get your result, because in order to produce that array of voids, you actually have to print the values, but this makes no sense whatsoever. I see this sometimes, and well, yeah, I look for some, I don't know, for some bleach to wash my eyes when I see someone using map instead of for each, because it's truly terrible. Okay, now let's have a little bit of fun. Let's remove this dire warning. Define an array of numbers or strings. Okay, so string or number. This still works. 1, 2, 3, 4. Okay, print all the numbers. Ooh. Okay, so now this is either a string or a number. So let's actually change its name. Let's call it x. If type of x is not string. Oh, I changed the font, by the way. I'm using Fira code, which makes me very happy. Which, when you put exclamation mark and equal and you put them next to each other, bam, you get a pretty mathematical symbol. When you put equal and greater than, you get the little arrow, and so on. Fira code is the best. Okay, now this, we need a block, because of course we cannot have an if in we cannot really have an if in side in an expression. And there we go. Okay, now I do hate blocks, so I'm going to do something peculiar. I'm going to define if as an expression. Yes, actually I'm going to do it. Okay, so if is going to be generic, because it is a generic function. Takes as input a condition. So, and the condition, well, it's generic in whatever it returns, whatever the if returns. In our case, what it returns is just void, but that's fine. So we take a condition. Let's actually make it lazy, so we accept it as a... wait, why is it unhappy? Okay, let's see if there's something else. Well, let's keep writing. I will look into this later, the condition, and then what happens if the condition is true. And this will be well, also a function that is only invoked and which returns a, but which is only invoked if the condition is true. Okay, and then we return a or undefined, or we could say a or void. Yes, okay. And here, what we're going to do is we check if the condition is true, then we return the invocation to the then, otherwise we return void. Void or undefined? I'm wondering though. Yes, it's also happy. There's no problem whatsoever. And now we can remove these curly brackets, and we have if, and of course we pass the condition, and the second argument we invoke console.log. There you go. so elegant. Okay, and now we don't need the block. And also, accidentally or not, we have seen that we can define if as a generic function. We can also define if else. And in the case of if else, we don't return undefined ever, because we have the else. Oh. Okay. Else underscore, because else is a reserved keyword, so I cannot declare a variable else. So if condition return then, else return else, and this I could just invoke. when I do actually have another branch. Okay. All right. Define a function which finds a number in a given array of numbers. Okay, so finds a number. So function find number which takes an array of numbers and returns found or not found. Okay. So it's actually quite easy. Let's start with a for of. So for x of numbers, if well, which number are we looking for? Searched. If searched is equal to x, return found, and otherwise return not found. And well, there we go. There's also let's do this recursively, but okay, this is an insane variant. So if numbers dot length is equal to 0, so the array is empty, the number can't possibly be there. So we return not found, because it's an empty array, so there's nothing to be found. Otherwise, if numbers of 0, so the first one, is equal to searched, we return that it has been found. Okay, very good. Otherwise, we skip the first one, and we continue searching by recreating the array without the first element. So numbers dot, do we have, okay, yeah, slice, very good, and we say, okay, start at 1 and make a copy of the array and go for searched. Okay, so and the reason why I'm bothering to do this is that now I can turn this into a single big expression. Yeah, sorry, that was it. And there you go. Okay, let's see if this one works. Console.log find number 1, 2, 3, 4. Not found. 1, 2, 3, 2. Found. This is a terrible implementation because it's a terrible implementation because it recreates the full array every time. Then again, recursion is nice, but for arrays and recursion don't work as well as arrays and lists, like for example from the immutable library. Okay, now define a function which calculates the minimum, maximum, and average of a given array of numbers. So we want all three of them. Okay. Min, max, average. Now we have an array of numbers, and we want to return. Okay, let's say data structure. Okay, for now I'll be lazy. Min, max, average, but this we should really return a structure, and this structure should be should have names, like it should be an object. Now, okay. In order to calculate the average, we need to add all the numbers together. In order to calculate the minimum, I need to track the minimum so far. In order to track the maximum, I need to track the maximum so far. Okay, now here goes nothing. Let's say that we have an accumulator, which are 3 numbers. The current minimum, the current maximum, and the sum of all the values so far. This could have better names, but I want to do this quickly because we have a mountain of exercises to go. Okay, so what is a good candidate for the current minimum? Well, actually, oh, and what if the array is empty? Well, if the array is empty, we just return undefined. So let's get this out of the way. If numbers.length is equal to 0, return undefined. The array is empty. We can't calculate it. It doesn't have a minimum, doesn't have a maximum, and it doesn't have an average. Okay, now that we know that the array is not empty, so we start with the input validation. The accumulator can start with the first values, numbers of 0, numbers of 0, and numbers of 0, meaning that we kind of skip the first element. So the first element, we take it as the first candidate, not because it's a good one, but because the array is not empty, and so it's the only one we can be certain about. And at the end, we just return the accumulator, but mind you, well, okay, so whatever came out of the accumulator in the first place will be the minimum, whatever came out in the second place will be the maximum, and whatever came out of the last element will be, mind you, the sum of all values, which we divide by the length of the array, and this is the average. All right, now for of, we check all the values in numbers. And okay, so the accumulator, oh yeah, obviously it's not a constant because it will have to change. Okay, so accumulator will be, well, the first value, oh, we're checking the first one again, and this is not good. So let's slice by 1, creating, so slice takes, cuts the array in and takes a subarray. So let's skip the first one, because the first one otherwise we add it twice. For the minimum and maximum it doesn't matter, but for the average it does, because we don't want to add it twice. Otherwise we get just a wrong average. Okay, now the first value will be the minimum between x, so this new candidate, and the accumulator at 0. The second value will be the maximum between x and the accumulator at 1, because accumulator at 0 is the minimum so far. The accumulator at 1 is the maximum so far. And finally x plus accumulator of 2. Well, we just add them together. Let's see if I've made any silly mistakes here. Min, max, average of 1, 2, 3, 4. Okay, let's think about it. So obviously the minimum will be 1, the maximum will be 4, and the average will be 2.5, I think. 2.5, right? Oh yeah, there you go. 1, 4, 2.5. Yay! Very good. All right. Now, let's continue with arrays. Define a function which adds all values within a given range of an array. Okay. Interesting. This isn't specifying what type the values have. Let's start with numbers, and then let's generalize a little bit. Okay. And within a given range of an array. Oh, this is going to be fun. Okay. Const add all. No, add range. Okay, we take as input the array. Let's call it values, because this is going to change. And this is an array of number. Then we want the range. Start of the range. I'll call it L for lower. And U. Call it U for upper. So start and end would probably also be good names. All right, now, if L is greater than U, then we're past the range. So we just return 0, because there's nothing to add. I'm also going to assume, but no, let's add some validation. If L is greater than U, then 0. But we also need to make sure that L is not negative and U is not greater or equal than values.length. So for now, let's write it optimistically, then we make it a little bit more defensive. Okay, otherwise, when we take the first value in the range, which is the lower, and we add it to the range of the remaining values, and because we already added the one in position L, we continue at L plus 1. We could also do it the other way around. We could go backwards. So we say, no, we add the last element of the range and we decrease the top of the range. I don't know why this looks ugly to me. So yeah. Okay, and this returns, I guess, a number. Okay. Let's run this. So add range 1, 2, 3, 4, but then we want to add elements 2 to 3. So the range from the third to the fourth elements. Let's run it and we get 7 because it makes sense. That's 3 plus 4. But what if we attempted 2 to 5? We get not a number because we're trying to fetch elements past the end of the array. Those elements have value undefined, and yeah, undefined plus number gives us this ugly none, not a number. Okay, let me see. Well, we could just be defensive and say, okay, if so we return 0 if L is greater than 0 or U is greater than values dot length minus 1 or L is smaller than 0. This is kind of too much. So actually, let's perform this cleanup before we enter into the thick of the function. If U is greater than values dot length minus 1, then we return add range but cleaned up. So with L and just values dot length minus 1. So we sort of kept it. Hey, why is it unhappy? Oh, yeah, of course, the values, yes. Similarly, if L is smaller than 0, then we add all the values, but instead of L, we pick 0, and obviously we keep U because U is fine. So basically, these first checks are, no, okay, we could also decide to move them up and separate this iteration logic, but that is perhaps too much because what I do want to show is something a lot more fun. Now we have this add range function, okay, which adds a bunch of numbers. But we can also add strings. And look, lo and behold, well, obviously this has to be an empty string. And, well, obviously this is now string concatenation. Okay. A, B, C, and D. Let's add to 300. So let's check our bounds. And we only get CD. Excellent. Okay. Very good. So, this is terrible. So let's restore it to 3. Okay, very good. But what if we wanted to have just one add range function which is capable of adding numbers, strings, or anything else which can be added? What really changes? Well, what changes is this. So the value when we reach, let's say, the end of the range or the empty range. And obviously this plus operator, well, it's not really the same, even though it's the same symbol on the keyboard. It's not really the same operator because the sum of numbers and the sum of strings are really, well, not the same. And there are also other data types which support something that could be sort of like sum, like arrays that can be concatenated, or booleans that we can put in or and so on. Okay, so let's get two. Let's make add range generic. So we take an array of A's and we return a single A. And the problem is, yeah, okay, now that it's A, it doesn't make any sense to add them, and also it doesn't make any sense to just return an empty string. So let's add 2 more parameters. The 0 value, or onEmpty, which is the value we return, and we have to pass it on every time. Yes, there you go. Which we return when when there is no range to add. So when we've reached the end of the range. And now, well, these here are basically two values of type A, the one on the left, the first one, and the result of compacting all the others. And we need to, well, add them together or squish them together. Let's call it squish. Let's have, you know, why not? And squish will take as input two values of type A and compact them down into just one. Now, of course, we need to pass a squish on everywhere, otherwise we get a complaint. And here we can just call squish of values of L and add range, and there we go. Now, add range of strings. In the case of empty, well, we just pass the empty string, and squish will be that we take two strings, let's call them A and B, whatever, S1, S2, and we add them together. And now add range works exactly the same. But, oh, and in this case, the generic argument has been guessed correctly to be a string just by virtue of the fact that the array is an array of strings. On the other hand, let's go put 1, 2, 3, 4, and here we get an error because the first element of the first parameter, the first argument we passed is an array of numbers. So now we guess, okay, this must be add range of number, but then the onEmpty parameter has to be a number. So there we go. And now we get 7. We could also have arrays. So let's say that these are arrays 1, 1, 2, 2, 3, 3, and 4, 4. What can we do with these arrays? Well, we can concatenate them together. Now A and B are arrays, and what we can do now is we can create an array with all the elements of A followed by all the elements of B. And yes, I'm dropping a new little bit of syntax on you. The 3 dots basically say, okay, within an array, create a copy of the array of all the elements in place. So now this is taking the elements in this range and concatenating them together, and the result will be, lo and behold, 3, 3, 4, 4. And now this add range function is really powerful because it can deal with anything that can be compacted or squished within a range. And that's quite a lot more actually than we bargained for. Okay. Define an array of polymorphic vehicles from the previous chapter. Print only the autos and scooters. Okay, now let's rest a little bit with a much easier assignment. Let's say that we have a vehicle, and the vehicle can be an auto, and then, yeah, you know what, I'll just replicate this very quickly. Can be an auto, a scooter, a truck, or an e-bike. Okay. And let's define an array of vehicles, and this will be an array of vehicle. Oh, and let's also say that all the vehicles just have, let's do this properly, apologies. No, we don't do things in a hurry, we do things well. The love for your craftsmanship. Okay, so all vehicles will have a brand and a model name. And then the auto will also have, okay, in this case I will just put some, now I will put some very silly properties just to make sure that we have to check on the kind first. So we have auto, which is a property that is unique to vehicle when the kind is auto. We have scooter, which is a property that is unique to a vehicle being a scooter, truck, and so on. Okay, now we can instantiate some vehicles. Kind, auto, then we have this silly property, The point of this property auto is that it's hidden until you've done the check on kind, because we're focusing on the check on kind within an array now. And then we have the brand, Fiat, the model, Panda, Cross, Glorious Auto. Then let's say we have another auto, Toyota Yaris. Then let's have a scooter. Now look, this property is not there anymore, so there is some polymorphism, even though it's not really meaningful polymorphism. Piaggio, and then of course, I mean, the Vespa cannot really miss. Let's have a truck. I really have no idea. Okay, what's a decent truck? Brand. Dodge, model, Ram. My deep ignorance of trucks is showing here. Okay, now let's be careful. If I hadn't said that this is an array of vehicles, then what gets guessed is really messy. This can happen when you have complex data structures. So look, this is guessing that the kind is a string, auto is a string, everything is a string, scooter and truck are optional. That's terrible. So by stating, okay, this is an array of vehicle, we are helping TypeScript tidy up what it guesses, because otherwise what it guesses is sort of terrifying. Okay, now let's iterate through the vehicles with our trusted for each. And now in the vehicle, well, we do have the brand and the model because they are always there, but the kind needs to be checked. So v.kind is now if v.kind is auto, then we can print, and in this case I'm going to print, well, you see there's the auto property because we checked, and v.brand dot v.model is an, and then the auto property else. And now let's check. v.kind is a scooter, and now we can log brand model is a v.scooter. Also notice that here the kind is scooter, truck, or e-bike because auto has been filtered away. Okay, let's continue our marathon. The next exercise requires us to define a function generic in T which accepts an array of tuples, each tuple containing 3 t's, and we are supposed to print all the t's. Okay, it's actually quite easy. Now let's start by defining a function generic in T. Print array, print triplet arrays. No, triplet array, because well, a tuple with 3 elements is a triplet. Okay. It's generic in T, so there we go. Let's add the generic type. Okay, now the values are, or the triplets actually, that's an array of a tuple, square brackets, T, 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 each containing 3 t's. Print all the t's. Well, for of triplet of triplets, and then for of, because we can actually go through the elements of a triplet, and now t here, x here has type t, and then console.log x. Okay. So that's a very easy way of doing this. And then print triplet array of 1, 2, 3, 4, 5, 6. Let's run this. And there you go. 1, 2, 3, 4, 5, 6. Amazing. Now that's one way of doing this. You might wonder, okay, so why is xt? Well, let me show you something else. Suppose that this were t number t, so we're deviating from the exercise. Now x is going to be either t or number. So when you go through the elements of a tuple, then the type that results, and it's the only type that TypeScript can actually guarantee, is the union of all the types of the different elements of the tuple. And if, say, the last value were a string, X is going to be string or number or t. Makes perfect sense. So another way of doing this exercise, not saying it's better, if we don't want to iterate, for example, because the types, the values of the tuple have different types, and we actually want to pinpoint which item of the tuple we're processing, then we can also use the composition. So notice that here I'm saying const xyz of triplets, because when you have a value like triplet here, we can perform a decomposition during assignment. Decomposition means that we put on the left of the assignment, and the assignment is also implicit here in the declaration of triplet and of, the structure that we want to read of the thing to the right. This is actually quite nice, because it's an alternative to the very ugly fetch all the elements one by one, which is honestly quite terrible. So we know that the triplet is built up as a structure, and here you can have actually anything you want. You can even have an object with curly brackets, for example. You can decompose however you want. It's a very neat and quick way of extracting plenty of values from the thing to the right into the structure on the left. Okay, that was easy. Now, this is very exciting. Well, no, not this bit. The first bit is super easy. Given an array of people, each with a birthday, find all the groups of people with the same birthday. Okay, so type person has just a name and birthday. The birthday, I'm going to just say it's a number, and this is just the number of the day in the year. So 1st of January is 1, 2nd of January is 2, and the last day of December is 365. Okay? So I'm going to keep it simple. And I want to group people by having the same birthday. For this, I am going to import map and list from immutable, the immutable library. Very handy. Okay, now I have a bunch of people, and this will be an array. No, let's say this is a list of person actually. Yes. Now let's create this list of people. Because there's also a second bit of the exercise, and okay, yes. All right, because we are also asked try running the previous exercise with a large number of people. It's probably very slow. So let's set this up already. Let's create. Let's create a range of a variable number of people. Map. Okay, and then yeah, okay, the name should be more or less random. We don't really care about this, we just care about the performance and the structure. So this will be a person number I, and that will be the name, and the birthday will be math.floor of math.random, which is between 0 and 1 times 365. Okay. And of course, this is a map. So to list. Now we have our, or just on second thought, let's have this an array. Let's make this into an array, because we are required to build an array. Okay, very good. So people numbered sequentially. Sounds like an alienating sort of a Stalinistic or Maoistic dream. So yeah, okay. Poor people in this exercise. Let's group them by birthday. Okay, so we start by iterating. So for let I is 0, I smaller than people dot length, I plus plus. Okay, we go through all the people. We're going to store the groups of people. So let's people by birthday. Okay, this will be a map from the birthday, and here on the right side let's have a list of person. Okay, and we start by map dot empty. We have map dot empty? No? Okay, just a constructor of map. That's good enough. Okay, cool. Now crap. I'm actually running this. I'm actually doing the second part of the exercise already. Oh no, computer science has ruined my ability to write slow code properly. Give me a second. Okay, no. This will be, yes. Okay, let's start. So this I comment away. Let's start by having an array of list of person. Yes. And this will be a range from 0 to, oh no. Okay, we will do this immediately the good way. No, it's actually harder to do. It's actually harder to do slowly in the naive way. What I wanted to show is it's basically the following. So the slow version and finding a way to implement this is a bonus exercise, because apparently I'm failing at this. But that's okay. This chapter is super long anyway. My point is that if you have to go through the people array twice in order to find all the people with the same birthday, then this will be insanely slow, because especially if the length is a bit large, especially if the length is oh no, wait, oh yes, got it. No extra exercise. Now I see it. Okay, very good. So I want to group people by birthday. Okay, yes. So here's what we're going to do. For every person, this person has a birthday. Yes, and now we're going to go through the whole array again, finding... No, actually, we can go through the array starting from the next person and gather all the people with the same birthday. Yes, got it. Yes, we can write the slow version. Oh, so exciting. Okay, the group will be all the people with the same birthday as people of I. Okay, excellent. And this group will be, well, this will be a list of person, and it starts off as an empty list. Then we go through all the rest of the people, and if... Oh, wait. Okay, so obviously the group is not empty because we start with people of I. People of I is already in the group. But then if people of j dot birthday is equal to people of I dot birthday, then we can add people of j to the group. Group is equal to group dot push people of j. Okay, very good. And then we would just print the group. Not that it's very exciting. let's be careful though, because we're going to find the same group multiple times. So the birthdays we have seen already. Birthdays already seen. Let's say this is just an array of, yeah, just an array of Boolean, and this is the range between 0 and 365, which initially we all set to false. And then we skip the whole thing if we have already seen people of I.birthday. So the idea is that in this birthdays already seen, we track whether or not we have already seen a birthday, because then we've already produced that group, you know. And here we would print the group. Okay, yes, this is the slow version. Let's start with a synthetic range, because we first want to test this. Name A, birthday 1, well, A1, A2, A3, B1, B2, C1, C2, C3, and finally D1 does not share the birthday with anyone. Okay, now we're going to print the group. Okay, so group dot join, and this will produce a string with the comma as default separator. But perhaps first we actually turn the group into just the names, and we do also print the birthday. So group dot first, which is definitely there because, well, we know we put at least people of I, or yeah, if we want to have this even more type safe, people of I dot birthday, and this is the group. Okay. Now, so what do we get? Oh no. Oh well, this is not really what I was expecting. Let's debug this. Okay. In order to debug, I'm just going to use print statements. So I'm going to validate every hypothesis. So processing person I. Oh well, this is refreshing, it's happening, and it's processing all 8 people. Okay. Processing person I because their birthday is has not been seen yet. Now we should see a lot less of those messages. Oh. Oh. Of course, if it has not already been seen, so I put the not, but okay, if this is false, of course, otherwise we skip them all. But the birthdays have not been processed yet. Oh, what a silly, silly, silly bug. Okay, there you go. So group 1 is A1, A2, A3, group 2 is B1, B2, group 3 is C1, C2, C3, and group 4 is D1. Okay, that was actually a lot less painful than I imagined this exercise would be. Let's put 100 people and let's not print the group, because printing the group is actually quite slow. Or, you know what, I don't care, let's print it for now. Printing can actually screw up the speed of your application. Okay, well, this was pretty quick. Let me also print the timing. The start is date dot now. The finish time is date dot now, console dot log. the program took finish minus start to complete, and okay, and this is in milliseconds. So let's divide by 1,000, and this is these are the seconds. Obviously, it's going to be fractional. Okay, so that was pretty quick. Okay, let's say 10,000. Okay, for 10,000, that's quite slower. Let me try again with 100. It's kind of funny. You see how slow console.log is now, because it was 8 milliseconds and now it's 1 millisecond. Okay, so it's still doable. Okay. Okay, now this is taken. Okay, so this is 1 million. Is it 1 million? 2. Yes, it's 1 million. So for 1 million, we are in the realm of 1.645 seconds. Okay. Now let's move to the faster version. The faster version. So this I'm going to comment away, or I'm not going to comment away. Const version, and this will be arrays or maps, and it's going to be maps. Then we can also play around with which version of the application we want to run. If the version is maps, otherwise we run the version with arrays. There you go. So we can switch and play around with performance. Okay, now. So we are going to have this map, which is an optimized container, and it's optimized when we want to access by number. And now we only go through the list of people once. So for person of people, the code also gets significantly simpler. So people by birthday is okay. Now, first we might want to check. No, not even actually. No, we have to check if the list of person is already there, because if it's for the first time we encounter a given date, then well, there isn't well, we have to add the first list. Okay, so if people by birthday has, so there is something at person of as at person.birthday, and this is false. So it's the first time we encounter this birthday. Then people by birthday, we set at the location birthday a list made up of the array with just person. So we bootstrap this element, because this birthday is empty. There is nothing in it. So we have to start by putting an empty list in it. And otherwise, no, there's update which does this. Actually, no. Update is even better. Oh, I had forgotten. Okay, so first we get the key, and the key will be person.birthday. Okay, then the value we want to put if it's not set. And the value we want to put if it's not set is the list with just the person. And otherwise, wait, why are you unhappy? Don't be unhappy about this. No, okay. And then the updater, which takes the previous list of person and does something with it, and the previous list of person we are going to push person. So, oh, very pretty. So basically what update says is, okay, on the location of this birthday, if it's empty, okay, then put this as a placeholder, just this person, because, well, it's empty, so it's the first time we encounter this birthday. Otherwise, take the list that's already there and push the person on the list. Okay, now the big question is how fast is update? And here's something you might want to know. The map container is optimized for being able to access the value, so the second type, by key, which is what update, get, has, and set do, without having to go through the dictionary, without having to go through the map. This is important. If this were an array, we would have to search for the birthday. We'd have to search for it, and this would mean we would have to go through the whole array, and we'll get an effect that is comparable to this for inside the for loop. And well, just to think about this, if there's 100 people, then the double for loop does roughly 100 times 100 iterations, which is a lot. But if it's 10,000, well, the zeros do tend to grow very quickly. And like in our case, if it's 1 million times 1 million, yeah, the zeros grow up even faster. Okay. And that's because of the second iteration. But because update doesn't need to go through any array, like this update, you can imagine there's an optimization. It's either a hash table, or much more likely it's a balanced binary tree, is an advanced data structure that is optimized just for speed. Update is super fast. So whenever you need to build nested for loops, and you see the possibility of simplifying with a supporting dictionary, you might want to do it. Okay, anyway, so now we have the maps. Let's see how fast this is. Well, it's significantly faster, like almost half, almost twice as fast. Okay, let's see how this scales, by the way. Okay, so this is 1.69, and let's go back to the arrays version. How silly. Really? Ah, okay. That would have been nice, but okay. So if false, and now we do the array version. Okay, so you can see that doubling the size, okay, this is funny. Doubling the size in the array versions brought us to 3.309, whereas going from 1 million to 2 millions goes from 0.9 945 to 1.8. And it actually makes sense, because the only thing that's going to affect the performance of this, if we assume that update basically always takes the same amount of time independently of how big people by birthday, how big people by birthday ends up being, because update is roughly always the same amount of time and it's super fast. So this is basically a constant amount of time. And so the size of the people array is the only thing that matters. And it's kind of funny, because we double the size, and the version with the maps sort of doubles. But actually, and if you were to plot this for the array version, it's not going to double. It's actually going to grow sort of, it's going to grow quadratically, because, well, we've seen the effect of the multiplication of the zeros. And well, let me see if we double again what happens, and then I'm going to stop. It's very important to keep in mind your supporting data structures, because this can make a massive difference in performance. Okay, so now we've doubled again, and here we are at 3.469 seconds, and this was the version with maps. For this one, we're probably going to have to go get a coffee. No, probably not. but the version with arrays eventually gets so slow that coffee becomes the getting a coffee becomes the only option. Okay, now we're at 6.567. So 567. Yes. Okay. So you can see that this is actually more dramatic, and it's not a factor. It's a quadratic growth. So as you keep plotting it, it will eventually really blow up. So this column will eventually start growing, grows a lot faster. So it's not just a multiplicative factor. Okay, this was fun. Maps for optimizations in the backend and the frontend make a massive, 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 massive difference. Okay, enough with arrays. We now move on to promises. The first assignment we get is to define a random number promise which waits for a random period of time between 0.5 and 2.5 seconds before returning a random number between 0 and 100. And we want to even print this number in a continuation attached with a then operator. Whoa, what a mouthful. Okay, so this is actually a super useful exercise for any web developer, or even for most people working with APIs, because it allows us to see how we can simulate delays. In most code bases, especially if you're building a front end and the front end runs API calls to a backend, and both the front end and backend are running on a developer machine, you don't see realistic wait times, because obviously it takes a fraction of the time we would take on the internet for two local programs, the front end and the backend, to talk to each other. By learning how to simulate delays, we can actually see how our application and what the user experience would actually be like with realistic delays. And that's also why we want to have a slightly random variation. Okay, it's a linear range where all the intervals, all the values of time are equally likely. But that's more than good enough. And then you can see if your spinners and if your logic for showing the user that the API call is running actually behave well. Okay, enough words. Random number is a promise of number. Okay, we just create a new promise with the new operator. We will see more about this new operator, by the way, in the classes about object orientation. Okay, now the promise takes as input, the constructor of the promise takes as input two callbacks, res and reg. If we call res, we have to pass it a number. Look, it expects a number, or another promise that returns a number for eventual chaining. And if we call reg, we can actually pass anything, usually a string, which tells the reason why the promise failed. If we call res, then whatever is passed to the then operator is going to be triggered with the argument of res. So basically res is a way to return. It's the same as return. So in a normal function you would say return 100, and here we would say res 100. Okay, very good. But we have to wait, and in order to wait we use set timeout. Now what does set timeout do? It takes as input a callback, and this block of code between the curly brackets will be called after ms milliseconds. Okay. Math.random produces a random number between 0 and 1. Now, we multiply this by, we want to wait between 0.2 and 2.5 seconds. So we're always waiting at least 0.5 seconds plus the remaining second multiplied by a random number between 0 and 1 will be a random number between 0 and 2. So this ends up being a number between 0.5 plus at the minimum 0 or 0.5 plus at the maximum 2, that is between 0.5 and 2.5. Now, after the random interval has been weighted, we invoke res. We might even have here a given probability with which this promise fails, like math.random, if this is greater than 0.1, so with a chance of 90%, we call res, else we call reg, but that's too much for this assignment. Okay, so we just call res with, again, a random number between 0 and 100. So math.random times 100. And now I want to make sure I return an integer. So I just pick the floor of this. Oops. Okay, good. Then I can call random number. And then simply I get the number and I just want to log it. So let's run this program. I don't really see the weighting. Oh my god, yes, of course we don't see the weighting because this is in milliseconds. So times 1000, because I meant seconds, but I actually have to translate it into milliseconds. Okay, now we get to see. Oh, 0. Okay. 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 And you can see sometimes it's slower, sometimes it's faster. Very good. Okay. Looks like it's sort of working actually. Okay. What if I want to call this promise multiple times though? Ooh. No, then we're screwed. No, we are absolutely not screwed. Well, first of all, I can simplify this slightly by putting the generic argument here. Don't need to declare this. And also I'm just going to put it into a lambda. This way, whenever I want to generate a random number, like this, because, okay, sorry, let me go back. If we were to do this, after the promise has been discharged, has produced a value, then if you then it again, you just get the same value. So this doesn't work. In order to fix this, we have to make the lambda lazy, meaning that basically we just hide it under the promise lazy, meaning that we just hide it behind the lambda, and then whenever you call the lambda, a new promise is instantiated. Yeah, and now perhaps I could also call it a couple of times, and we should see 3 different results, because every time it's a different promise, and so we don't get to see the previous result of the same promise. So we are re-instantiating the promise. Whenever you want to have a local promise that needs to be instantiated, it's a good idea to remember, if there are arguments or a function call before the promise gets re-instantiated. If you end up accidentally returning the same promise twice, on the other hand, you will not restart the promise and whatever it does. So just be careful, be aware of this. Okay, now, oh, look there. At a 10% chance that the previous promise fails. This is also good, because otherwise when building a sample promise with sample data for our frontends for mocking purposes, for example, it's very difficult to actually see errors happening. And then in production, you will see for the very first time, or you will be able to test for the very first time how the application behaves when there are errors. And that's actually not ideal. You want to have control over this. So that's also why we say that in general, mocking is quite important, and mocking has to actually make sure that your program gets tested with all the possible scenarios and not just the happy path. Testing only with a happy path is kind of pointless. Okay, so if we generate a random number between 0 and 0.9, so with a 90% chance, we just return the result as we just did. Okay, otherwise we reject and say error. Okay, so there was an error. All right, now we want to print the error. And printing the error is done very simply by adding a catch statement. And here we can say console.log. There was an error. And then we can simply print the error message. Okay, now we can remove the other 2. Let's see what happens now. 81. 14. Let's reduce the interval. So between 0.1 and 0.4. So between 1/10 of a second and half a second. Now we get a faster tests. There was an error. There we go, in catch. Okay. Now let's see async await in action, because they make especially consuming promises much easier. Okay, define an async function which invokes the random number promise with the await statement and then print the results, catch errors with the normal exception handling of TypeScript. Okay, so const call random print random number with delay, and this will be an async function. So we just declare it as async. We can also do this with function. I'm just building a lambda because I personally like lambdas more, but yeah, again, your mileage may vary. Okay, so now we await random number, but we also want to get the result. So I'm going to say const underscore is equal to await random number, and underscore will be, lo and behold, oh, well, we've lost the fact that it's a number, and that's quite bad actually. Okay, now. Because I left the then and the catch. Okay, no, so we didn't lose the fact that it's a number. At least they should know. Let's check. Random. Oh no. Let's leave the number annotation. I understand why it could be difficult to for the TypeScript to actually guess that, because we're passing a number to res, then this bubbles up to the fact that the promise was supposed to be a promise of number. So I get it. And so either we put it here, or we put it here. Yeah, however you prefer. It depends. If the type is rich enough, I actually prefer to have the type neatly separated from the definition of code, but I digress. So underscore now is a number. That's the number coming out of the await random number. So this combination here, so let or const is equal to await followed by promise, is exactly the same as the promise dot then the argument. So this argument with underscore is the same thing we put in the const, but it's just much more natural because it looks like an assignment where await is sort of, you know, mediating the assignment, but we don't need to have the whole then ugly thingy. And now try, because this might throw an error, catch and then underscore, and this underscore here will be the parameter of the catch, so it's the variable that is passed is the value that is passed to the catch callback. So again, this value here, and then we can print the error. This may look a little bit more verbose, but oh, it's such a pleasure. It's so much cleaner to read. Can I just say, oh yeah, now this is a function, and now I have to call it. Just call then, and just calling then should be enough. And there you go. I want to see the error at least once. Oh, come on. Oh, come on. Okay, so, oh yes, fine, there was an error. So all the paths have been triggered, and there you go. Now, if you're consuming promises or multiple promises, yeah, using this whole try, catch, and await, it's a breeze. Just be aware of the fact that what you get out of an async function is still a promise, because in order to be able to await, you need a promise. So that's why I have to call then here without parameters, just to say at some point, because print random number with delay doesn't run a random number, obviously, it just creates a new promise that will run a random number when print random number with delay is actually activated. But I can't just call the function. Oh, I can actually. Oh, I can, and it gets... yes. Sorry, by calling it, I actually instantiate it. That's my bad. Yes, okay. But by not calling it, of course, it doesn't instantiate. Yeah, so the then was actually superfluous. My apologies. Okay, anyway. Now, ooh. Okay, promises happen to have a couple of interesting utility functions, all and arrays in particular. So arrays gets as input an array of promises and it creates a promise that is resolved or rejected when any of the provided promises are resolved or rejected. So basically you have a bunch of things, like imagine you have a series of backend services and you call them all, and just as long as at least one says that they're done, that they've received your message, and processed it either correctly or resulting in an error, then you're happy. You don't care about the others. That's what Race does. And we are required to define a function any which takes as input a generic array of promises and returns the first promise which triggered successfully. And triggered in this case actually means then or catch. Okay. Now let's mark our random number generator so that it generates strings which contain this mark so that we can actually recognize which promise triggered, because we need to generate multiple promises. Okay, and we have an array. Let's create the various promises, and this should just be a random number, and the mark will be A. It's like a sort of a specific identifier of the promise. Random number of C and a random number of D. And you can imagine if we run all of these at the same time, it does stand to reason that what's going to happen is that, well, there's a delay, so we don't know which one is going to terminate. So every time we run these concurrently, well, another letter should appear. And let's also use the mark in the error so that we can also see which one errored out. Okay, so we want to define any, which is a generic function, takes as input an array of promises of A, and returns just one promise of A. Okay, well, you know what? Let's just create this promise that we're supposed to return. We have a result, or resolve and reject. Okay, very good. And now what do we do? Well, we actually just wait for all the promises. Okay, so let already triggered will be false, because no promise is triggered already. We have to trace this, because otherwise we don't know if the first promise has already triggered. And if the first promise has already triggered, then the others also come with an answer. We don't want to, trigger on those answers as well. Okay, good. Then the promises for each promise, we say, okay, promise.then. This is the result of that specific promise. Now, if we have already triggered, then that's it. We don't do anything. Otherwise, already triggered is now true because, well, one promise has triggered, so the others have to, well, be forgotten. And then we call res on the result. Of course, the promise might also have failed with the error, and we do exactly the same in the error. And we might refactor this code so that the management of the trigger of the already trigger, so this little bit of repetition is a tiny little bit ugly. You know what? Yeah, let's do this properly. Okay. Oh no, we can't really do this properly because we have to actually return. So no, we leave it like this. Okay. All right, and then we just call any. And well, this is a promise, and it's a promise of what? Well, of string. Okay, so in this case we print whatever result came or whatever error came. And we don't really distinguish between, so we just print whatever output we got. But obviously, I mean, in a real life application, we would have a slightly different response between then and catch, but we don't care. Let's see. Okay, D95, C18, D2, D35, C5, C47, B4. and so on. And it looks quite random to me, actually. And there you go, that's any, which is exactly the same as promise.raise. As always, I find it incredibly important, really important, that whenever we use a library, we know how to build that library. We shouldn't build all libraries, that would be insanity. These libraries are built so much better than what we can do, with a lot more edge cases and a lot more controls and a lot more testing. So we shouldn't, but we should really, so libraries and frameworks should never be a black hole of knowledge. It should always be something that we understand, we know, but we don't have the time practically to build it ourselves. Okay, now we have to do the same, but we have to define a function all, which takes as input a generic array of promises and returns a promise which triggers with the array of all results. So now we have to wait for all of them. Ooh, okay, so I'm going to be lazy here, and I am going to say that all takes as input the array of promises and returns a promise of array of A. Well, there's some intriguing mathematical elegance and symmetry here. Okay, so, well, not really already triggered, but so here we stored the results so far, and this will be an array of either A or now let's type this even better. Kind result and value will be A for the ones that triggered successfully, and kind error and message and reason message will be any, because that's the type that comes out of it. Okay, and you know what? I'm actually going to use a map from the index of the promise into whether or not we have a result yet. Okay, so for each promise we just run it, and then we wait for it with then. And then we either get a result or catch. Now, we don't really have an if already triggered, and we definitely don't trigger the result in then and catch like this, because we need the whole array of results. So what do we do? Well, for each also has a variation which takes as input the index. Oh, no, the index is the second parameter. Yes, very good. So this is the index of the promise. So promise I has produced either then or catch. Very good. So result so far dot set at location I. But in this case we have a result, and the value is result. And then of course we have to save this. In case of error, well, we set at location I an error, and the reason is error. Okay, cool. But right after performing this set, we also check result so far dot size. That's the number of entries. If the size is equal to promises dot length, then every promise has triggered. So now we call the result callback. We take the promise, results so far, which is now complete. We get all the values, and we turn it into an array. Oh, and it's unhappy, very unhappy. Okay, now let's play around with this a little bit, because now I have to get only the values. Okay. So I don't care about the keys anymore. Okay. So result so far. What if I just took the values? And values is now. It's an iterator. Okay, that might actually be what we want. Oh no. What about the value sequence? It always screws me a little bit. What happens if we just turn this into an array? Then we get an array of this looks This is the, oh, I should have read the error. Well, we get an array of this, obviously, but we said we would return an array of A, so no. Promise result of A is this, and we return a promise result of A. And now we can also remove this very ugly declaration. There we go, promise result of A. Yes, okay. Now, this is a little bit dangerous. Now this value sequence, yeah, it says it's indexed, but no, let's also do this a little bit better, because the these promises that we are getting, these promise results that we are getting, they also have to be in the same order, otherwise we get them in a mixed order. You know what, I don't care, but just so you know, we would have to order them. So this is not an entirely proper answer to the assignment. Okay, and then, oh yeah, we also pass res here, because this promise always succeeds. It's the underlying promises that might have failed. Okay, ooh, let's run it. Exciting. Oh well, oh, they all triggered with the result, and you can see that the order is screwed up a little bit. But we get every time all four of them. I would like to see an error. Yes, we have an error on A. All right. The reason why the order has been screwed up is because, well, the map is an associative container. It doesn't really promise anything about whether or not it will store the values in order by key, in the order of the keys. So it associates the keys with values, yes, but it doesn't guarantee anything about the order in which the keys and the corresponding values are stored. So let's actually see if we can fix this better. Okay, now let's turn this into a list. And now this is a list of what? Let's see. I just want to see the type, because the type of turning this into a list, okay, this is again a list of promise result. No, this is not ideal. So let's say that we have these promise results and the key. Okay, now this is interesting. So I have the value and the key, and now I want to keep both the key and the value together. And now if I call to list, now this is a list of, oh, so annoying. Okay, now as, and this is a tuple of number and promise result of A. What do I get now? Finally, I get a list where the entries are the number and the promise result. Okay. Now I can finally, can I order by here? Oh yes, I can sort by. Okay, very good. So I get this value, which has the key and the value, and I want to sort by key. Okay. And then to list. And then actually to array. And then we want to call res on this temporary variable. Okay. Oh, haha. Well, almost, because now we have to forget about the key. So we have the key and the value here, but after having sorted, I can simply focus on just the value. And what is temp? Oh, and that is surprising though, because the value is just a promise result. Okay, this. Let's do it twice. This is quite puzzling actually. So. Because the map. Okay, now let's play around with this. Okay, so the slight challenge is that the key now is a number, and the map actually also proposes to get the number. No, so okay. let's disambiguate this. We have a KV, and let's take a look at KV. So now this is the tuple number of promise. We're not taking any chances here. So I just take the first value, which is the number. Sorry, the second value, which is the key value, and oh, it's still unhappy. This is really surprising me. Now this. Oh, do I have to do it twice? Oh, wow. So if I don't do this, I get the number twice because it's the keys. So the first one is the keys. Oh, and the second, ooh, that's messy. Okay. Now, we do want to discard the keys those, and then here we might actually just go for the value sequence. And do we have the right one now? Ooh, okay. Wow, that was a lot of work. And now we can give the result with temp. Let's test this. A, B, C, D, A, B, C, D, A, B, C, D, error. Okay, the error bit is actually quite random because here we're not doing it properly. Okay, this we might want to generalize. We really should generalize this into little supporting functions, but okay, you know. For a throwaway exercise, that's acceptable. And now we simply, oh yeah, and we also call it as of result so far. And now they are always in order. Okay. Ooh, that was challenging. But just so you know, we map. So we take the values and the keys, and then we just join them together in a single value. Then we sort by, and we take these entries KV, and we say no, sort by the key. Then we take the key and the value together, and we just forget about the key because we don't care that much. And then we want all the values, which should be sorted now. And then we return the corresponding array. Ooh, let's run it again. Should produce the same result: ABCD, 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 ABCD with the error. Okay, it looks like it is working. Ooh, that was a lot of work. We will now use the containers from Immutable.js. The containers from Immutable.js are very important. They are very commonly used, they are very good implementations, and as such, it's a very good idea to actually learn a little bit about them. Okay, so we are asked to define a stack of person, fill it with the push method with 10 people, and extract them one by one with top and pop. And the question is, in what order are they coming out? Is it the same order in which we inserted them, or the same order in which we reverted them? The same order in which we reverted them, or the reverse order. And well, let's do this. Okay, so type person, name, and age. Oh, number, no, number. Okay, let S is a stack of person, and it's an empty stack. I'm just saying new stack of person. No. Okay. Then s.push, and then we add name will be person 1, age 22. Now, because all the containers of immutable are immutable, when we say push, we don't modify s with s.push, but rather a new stack is created, and without even a copy, by the way, but by cleverly reusing the old instance of s plus some extra data, so this doesn't waste memory or performance, and we have to assign the result to another stack, or in this case the same stack, because we don't really care much about it. We don't care about keeping track of all the historical values. But for example, for an undo buffer where you can actually undo operations, having a stack of operations might actually be very useful. And then you might actually want to keep older data structures because it doesn't really have any added cost with Immutable.js. Okay, now while s is not empty, we print s.top, s.pop, pop. Okay, and s.pop gives us, no, wait a second. S.pop simply gives us the new stack by removing one person, and I was really expecting s.top, to be honest. No top. Well, it's quite a bit far from the standard. Let's see what's in the collection. Yes, I would like to see the definition of the stack. Oh, yes, interface stack. Okay, so we have, oh, peak. Peak and first. Very good. Okay, no problem. Peak takes a look at what is the element that's about to be popped. I'm going to adjust the text of the exercise. Peak, not top. Yeah. Okay, and let's see what happens. Oh, we see 3, 2, 1. Okay, so the stack, like the name suggests, behaves a lot like a stack of heavy things that whenever you push another item on top of the stack of heavy things. So when you peek, the first one that comes off is the one on top, so the last one. The stack is called the LIFO, L-I-F-O. Oops, LIFO, which stands for last in is the first to come out. We also have FIFO, first in, first out. That would be the queue. FIFO, first in, first out. And yeah, depending on the scenario. So if you have a queue and you want to do so that, for example, you have a, I don't know, a queue of messages or operations that have to be sent to an API in the same order in which the user requested them, then you need to use a queue, for example. So if the user wants to, I don't know, modify an order and then change the address, and these are two separate API calls, you might have a queue of API calls and you execute them in the same order in which they were added to the queue. Whereas for a stack, the stack just behaves, just behaves in the opposite order, and the queue and the stack are optimized for big sizes. So if you want a stack behavior, you can simulate it with a queue, but it's going to be a lot slower because the queue is optimized for FIFO and the stack is optimized for LIFO. Okay, now let's play a little bit with lists and maps, because lists and maps are the cornerstone probably of Immutable.js. Okay, we have to define a list of numbers, fill it with numbers, and print them all with for of. Okay, so let's do this. Let n is a list of number, and then n is n.push. This is the very same n, but the same push method of a stack. N.push, so it pushes at the end. N.push of 2 and push of 3. Notice that again I have to save the new list in the same variable because I don't care about the old instances of the list with the less elements, but they are still there. And well, for safekeeping purposes, you might actually want to have an array of lists which represent all the stages in which the list has been built. Okay, I want to print all of these numbers with for of. So for each const x of n, console.log x, and we're going to get 1, 2, 3, 4, 5 on the screen. Okay, not very exciting. Now increment all numbers by 1 with map. Okay, so n is equal to n.map. Map expects a lambda which defines what to do with every value. So we get a value, let's call it x, and I would say, okay, increment the value by 1, and let's see what happens now. 2, 3, 4, 5, 6. So map is one of these bulk operations, these bulk higher order functions that process the collection at all of the collection's elements at once. And now we are supposed to remove all the numbers divisible by 7 with filter. Okay. Oops. Filter all numbers x such that modulus 7 gives 0. Okay, let's add a few more numbers, because otherwise we're not really going to see anything interesting. So 5, 6, 7, 8, and the only one that's divisible by 7 happens to be 7. Oh, haha. Remove all numbers. So the lambda we give to filter, which is called the predicate, tells which numbers do we keep, and in this case we keep the numbers that are not divisible by 7, so that's 2, 3, 4, 5, 6, 8, 9. Notice that because we first did map and then we did filter, the number that's the entry that's being deleted is not this one, because this becomes 8 because of map, but this one, which became 7 because of map. And well, that's it for this exercise. Okay, now instead of creating the numbers manually, use range to create the range of numbers and turn it into a list with 2 lists. Okay, now oh, this is also interesting because n. Okay, no, now it's a list. That's cool. But if we create, for example, numbers with a range, what we get is another type than list. So let's say that we want the range from 1 to 100. Now the type of n is not list, but it's indexed. Indexed means that we don't really contain the numbers 1 to 100, but rather we just contain the instructions. And the instructions are range 1 to 100. So it's the recipe for creating the range, but not the actual range. We can turn it into a list, which is going to eat up more memory, but well, the recipe requires a bit of computational power later on if you want to go through the list. But if you turn it into a list with 2 lists, you're basically sort of memoizing the sequence. So you're eating up memory, but you do not need to calculate the sequence anymore. For the range, it doesn't make a lot of different, but for things that require a little bit more computational power and processing, turning it into a list and then reading it, for example, many times will be faster than having to recalculate the whole sequence every single time. Okay, now we can run this, and well, there you go, we see a bunch of values, but for example, let's see, well, 70 is missing because it's divisible by 7, because the filter is still there. Now, oh. Okay, now. Now we're going to talk a little bit about performance. We're going to fill up a set with 10,000 random numbers and perform 1,000 lookups of numbers. And then we'll do the same with the list. So we're basically going to ask the question, is this number in the list or not? And in this number in the set or not? And let's see which one is faster. And then we'll talk about why. Okay, so the list will be, well, we start with an empty list. And the set starts off as a set of numbers. Oh, we do need to import a set as well. Okay, so for let i0 smaller than how many? Let's put a few more already. Let's make it a big set. And then we get a random number between 0 and I don't know, 100,000, and then we add this random number to both the list and the set. Okay, so now we have this. Now we have these random numbers in the list, the same random numbers in the list and in the set. Let's also take the floor, because otherwise the chance that we actually find a number is almost 0 because of the density of floors. Okay, now let's look these numbers up in the list and let's look them up in the set, and we do it separately. So start will be date.now, and this is in milliseconds, and is date.now. Now this will be the list lookup. So then we say the list lookups took, and then end minus start milliseconds. Okay. Now we have the random number, and now we want to know if it's in the list. So we want to know the Boolean. list dot, or no, better yet, let's just count the matches. If list dot fa has, and if it has r matches plus plus. Okay, we randomly imported assert. Okay, let's put this into a scope because I want to just copy all of this bit of code without having to reassign the variables, because I don't really like it. And then set dot has, and then the matches. And let's check this out. But I also want to parameterize things a little bit. Okay, let numbers, and let how many numbers. I want to parameterize this first thing. Yes, there we go. And then also how many matches we or how many searches, because I want to play a little bit with these parameters and see. Oops. Yes. Okay. And this is how many numbers. Okay. Now this code is a bit cleaner. Let me start with okay, 10,000 numbers and 1,000 searches. Okay. Oh wow. So the list lookup was actually faster. It's quite impressive. Let's say we want to do a lot of searches. Okay. Now this is very far to what I was expecting, to be honest. Okay, okay. But let's see. Oh. Oh, crap. Yes, I'm using the wrong one. All right, so, yeah. Okay. Has checks the key. Now, a list is considered to be a collection where the index of the element, like in an array, behaves as the key, which doesn't really say much because we really want to know, I really want to check, to look for the value, and looking for the value is the slow thing, because in the list we actually have to go through the whole collection. Okay, attempt number 2. So I was really, so because the list contains numbers, then the keys and the values have the same type, and now we see the proper results, because obviously the answer to, hey list, do you have key number 5? You just look at the length of the list, and if the length is longer than 5, then hey, yes, we do have key number 5. But we actually want to force the list to look at its values, not at its keys, because the keys of the list mean nothing whatsoever. Okay, so now with includes we are actually looking for the value. And okay, you can see that the list takes 3 seconds already for 10,000 lookups. And if we reduce the lookups, okay, it's about 1/10. And let's increase again. Now this is going to be quite impressive. It's probably going to be something like 30 seconds. No, even more actually, I'm guessing. And you can see that the list performance goes up very badly with both the number of searches and the amount of numbers, because every time we call includes, we just have to go through the whole list. And so this means that we perform how many searches multiplied on, in the worst case, by the number of numbers inside the list. Oh look, 30 seconds, but look at this. So I multiplied the searches by 10, and we went from 3.5 seconds to, okay, 35 seconds. And the set went to 10 milliseconds, which is nothing, to 20 milliseconds. So the set and the list are both going to be searched 10 times as much, but we don't get code that is 10 times slower for the set. The set is only 2 times slower because the set uses some very clever algorithms. It basically has a tree structure, and the tree structure, well, doesn't grow in depth linearly with the number of elements. So if you double the number of elements, the depth of the tree doesn't double, and the searches go through the depth of the tree. We will actually have an algorithms course in the academy where we will explore this in depth, but for now know that searching in a set is much faster than searching in a list. Okay, the next exercise forces us to learn a trick taken from the books and the theory of SQL databases, just in memory. We're going to use map to define a map of users, each with a unique ID as key. The ID is a string. It should be a GUID or something else. It should be a GUID ideally, but for now, let's just say it's a string. Let's also define a map of addresses. Define a list of, obviously the addresses will also all have an ID. Now define a list of users and addresses, which is simply 2 IDs. Now print the name of each user and the name of the addresses to which the user is connected. And the hint is use a temporary map rather than list for faster storage. Okay, now let's define type person, person, and this will just be an ID, which is a string, and let's say just a name. Okay, we don't really care that much about the extra structure. And the address will also be an ID, street, and number, and this is just going to be a number. And again, I'm not really caring much about how faithful these data structures are because we really want to focus on storage. Okay, cool. Now, let's define the people, and this is a map of person of ID and person. Actually, I was expecting IntelliSense. Yes. Now this is kind of cool because we're stating, okay, given type person, which is a record, get the type connected to key ID. So if we change it later on, if we say, nah, you know what, we're going to go, well, okay, it's not going to be better, but we want to change the type of ID, then automatically the map people adjusts as a consequence. So that's nice. Okay, then we have the addresses, and this is a map of address of ID, that's the key, so just string into address. And finally, let addresses by person, and this will be, now, okay, so this will be the addresses connected to a person's ID. Let me think. Yes. So, we focus on a person, and we make it easier to answer the question which addresses are connected to a given person. But I just made a mistake because we are going to store the IDs of those addresses, because an address might be also used by multiple people. Okay. Very good. Now, people, let's add. Let me think. How are we going to do this? Because I also want to generate the people and the addresses randomly. Yes, okay. People will be, okay, let's generate 10,000 random people. And obviously, the assignment is very rightfully complaining. Okay, then we have the index. I'm actually going to abuse the index. So the best indexes, so the best IDs are GUIDs, like big unique strings that act as identifiers, are unguessable, they are safe, they are not sequential, etc. But for now, I'm just going to basically create a string, which is person and then the index, and this will just be the GUID. So very ugly GUID. The ID will also be the same, and the name will be very unexciting. So person I. Still doesn't work, of course. Now this we're going to cast to a pair of person ID and person. And now, oh, missing a square bracket, because otherwise TypeScript is going to assume that this is an array of either string or, and then ID string, name string, which is, well, simply not expressive enough. And now it should be actually possible to say that we convert this to map, and yes, oh no, what a disappointment. So map number string person, it's not assignable to type map string person. Let me turn this into an array first, and let's see if perhaps it's better to create the map with a constructor. Yes, okay, cool. Okay, so what I'm doing here is I'm creating an array of 10,000 numbers. These are the IDs, and then for every ID I create a tuple of the ID, so the key and the value. So I have an array, and so what I end up having here is an array of keys and values, and if I call the constructor on this, it actually types correctly. And look, so if I were to put this in a temporary variable, then you can see that we have a map of string of person, because I had an array of string person tuples, and if I pass this to the constructor, I get a map of string person, okay, which I can assign. Very good. So I know that my keys are going to be person of 0 through person of 9,991. Okay, let's have some random addresses. We do roughly the same. Well, let's say we have even more addresses. Obviously, the system is unhappy. No problem. Now we have the street is going to be street, and then the number, and the number will be I modulus, I don't know, 300. Okay, and we cast this to address of ID and address. Why is it not happy? Oh no, now it is happy. Okay, very cool. So actually the cast was dictating the structure that we were expecting to the left. That's actually very, very cool. Okay, now we can actually bind the addresses by person. So addresses by person will be, again, create a map. We create, I don't know, because people can also be connected to multiple addresses for all sorts of reasons. We create the array, we map. Okay, now we have the index, and now we have to create, look, a map of person ID. So we have to create a tuple where the two elements are person ID and list of address of ID. Okay. I'm going to simplify something, actually. If we want to connect a person with multiple addresses, there will be multiple entries here. That's better. Okay, so this we're going to cast to a tuple of person of ID and address of ID. I'm actually quite happy we simplified this, and then this will be the key I need to generate, but it's not going to be person of I, but rather person of math dot random times people dot size, and of course convert it to floor because we want integer numbers. And the other will be address dash, and then we do roughly the same, but obviously with addresses dot size. Okay. Yes, let's give it a new line so that this remains a little bit readable, and there we go. Okay, now let's go through, let's print for every person the addresses of this person. So, oops, for person PE of people, actually dot value sec, because I just want to have the actual people. So the type of P, let's check very quickly. It's person. Okay, very good. Now we want to find all the addresses of this person. Very good. So Oh no, how silly. Of course, this doesn't really work. No, then I have only one address per person. Okay, for now, we keep it like this. Then we fix it. No, so the list setup was better. Because obviously the key is unique. How insanely silly of me. Okay, so now we find the address, A, and well, there might also not be an address, so I have to check if addresses by person has p.id. Then I have the address, and address will be addresses by person dot get p.id. And then let's say we count the matches. Just like we did for the other exercise. Okay, let's put this into a little block. Good, then const start is date.now, because we also want to time this a little bit. Okay, const end is date.now, console.log, and map took and minus start milliseconds. Okay, very good. Now though, I'm also going to have the addresses by person in a list. So it'll just be a list of, the person and the address connected to each other. And I'm going to run basically the same code, but addresses by person list, and it's not a map obviously, so we do create this tuple, and then at the end we convert to list. We don't need to turn it into an array before. Okay. And now we're going to see which one of these is faster. Okay. Now addresses by person list. Yeah, okay, now we have to actually find the entry. So let's say let's see what find takes as input. It takes, okay, a predicate that takes the two keys and says true or false. So what we're going to do is we're going to say that the address comes from finding, and then we have the person ID and the address ID, and we are looking for an entry where p.id is equal to person ID. Okay, and then A is going to be possibly undefined. So if A is not undefined, then we have A. Oh, sorry, let's say a person address. Okay, and then A is simply person address dot one. We might actually want to refine this even more. So because we also have the addresses, and ideally we wanted to also fetch the address. So let's also say, okay, then addresses dot get. So we actually fetch the address. Because this might be undefined. Okay, we know it's not undefined, so I'm going to put an exclamation mark, which is a potentially very dangerous thing, but we are inside a has block, and so we are pretty solidly certain that there is no reason to further check for undefined. Otherwise, we could say, okay, const person address is, okay, we just get by person ID, and then if PA is not undefined, and now the two implementations are actually very similar, so we get rid of this very ugly exclamation mark, and PA, well, this is the, no, this is just the address ID. Okay, so if the address ID is not undefined, good names, very important, then we can just fetch the corresponding address, and in this case, PA is actually the tuple, so very good. And now we can fetch this, and we can trust that it's there. So I'm actually going to put the exclamation mark, but in this case we might also want to have a double check. Let's run this. Okay, the map took 24 milliseconds. The list is probably going to take a little bit longer. I'm hoping 5 seconds. So maps, just like sets, are optimized to answer the question, So this get method is super quick, even if the address is by person. And you can imagine how many links do we have between address and person? A load, like so many, because especially if we want to represent a sort of all these networks, there are plenty of possible connections, and get is super optimized. It uses, again, the power of search trees, which are an optimization technique in algorithms and data structures that makes the speed of finding, in this case, an entry in addresses by person by key, by person ID, almost independent on how many addresses by person we have. Whereas in the case of list.find, list.find in worst case has to scan the whole list, and the bigger the list, the more it's going to take to scan it. And you can see that the difference is insane. Like, can you imagine? 24 milliseconds in human terms is almost instantaneous. Like, you almost don't perceive that you had to wait. 5 seconds. That's, you know, significantly beyond the kind of timings that people actively complain about. So yeah, this is a really powerful optimization technique. The reason why I also mentioned that this comes from the world of databases is quite simple. The primary key in a database is actually used to speed up access with a so-called index. And indices in databases very often are implemented with the very same, or very similar at least, binary search trees as a map in a dictionary. So by using maps for speeding up search operations in memory, you are leveraging the same very well-proven optimization technique that we have known in databases for, well, a few decades now. So you have the power now, use it wisely. I would say this concludes the practicum on generics. The practicum on generics is super important because for the first time in the course we also start using real-life data structures, and those real-life data structures that come from the big popular libraries usually are generic. So there is a connection actually, because if something is popular and pops up into many places, the chance that it's based on generic types is actually pretty high because, well, in order for something to be flexible and universally usable, its ability to represent different contents and process different values depending on the domain must be granted by generics. So yeah, it's not a random coincidence. Okay, and next class will be about object orientation. So we continue our climb towards more and more professional topics. Thank you very much for listening. Thank you very much for putting effort into this, and the best of luck with your own studies and career.